Yeah. So my name is Zhiwen, and I'm currently the assistant professor in the ECE department. I work on computer vision and multimodal generative model AI. So today I'm going to introduce my work about learning the physical world in 3D from real-time algorithm to scalable data curation. Yeah, let's get started. So nowadays, the advancement in foundation model, like GPT for languages and clip segment editing for images, have significantly how we work with the image data and text data. And we can now create the high-quality image from very simple descriptions using the generative AI technologies. And we can also handle a wide range of image and video understanding problem using the segmentation model, let's say from meta segment editing. Yeah, so but real world AI doesn't stop at 2D. So I think there are something called block.
Oh, yeah, let me hit this.
Okay. Yeah, so but real world AI doesn't stop at 2D. In everyday life, we rely on the geometry and the spatial relationship to interact with the physical world. So in robotics, autonomous driving, extended reality, also everything happens in 3D place.
I think I had to exit out the application.
I think there is, maybe I need to go to my second screen.
Right? Sorry about that.
Okay, cool.
Yeah, okay, great.
Yeah. So that's why because we are living in the 3D physical world, we have the static 3D environment and we have the dynamic subject. And that's what happens in physical world. So how the computing system to observe this? Because here is the observer, and we have a camera, and we can take the photos of the real world. And we really want to recover the static 3D environment and the dynamic actors, and even how the observer moves from image alone. So that's a definition of the problem. And we have many kind of sensors from mobile phone to headset and to robot cameras. So they are relying on their vision system to perceive this world first and then make decisions, right? So that's why this is the overview of my work. We will first introduce about the real-time 3D modeling because let's say for human, we indeed can process the visual input and we process in real time and we extract the content from the image alone. And then with such useful information, we can use our body to interact with this world. So that's why first, that's a 3D modeling part. And next, we have modeled the 3D. We can build the digital twin. But how can we display? How can we allow the user to see the digital twin? Let's say when we use the mobile phone and when we use the headset, so we are seeing the 2D display. But how can we flatten the 3D world, 3D digital world to 2D? So that's the second problem, real-time rendering. And next, as you may know, generative AI is data hungry. And people are trying to curate so many data for language model, for video model. But if we going to allow the computing system to really functional very well in the physical world, so it has to understand the 3D, and we have to have many data about the static environment and about the dynamic actors. So that's why the next part will be data curation. How can we create a lot of data for the generative model, for the multimodal models with the understanding about the real world and the dynamic actors. And for the last part, I will introduce my work to apply for the scientific data processing. Let's say when we deploy a rover on Martian surface, so can we build the digital twin on Mars, let's say beyond just the Earth? Yeah, so that's the overview of this seminar talk. But before we get started, let's first review multi-view geometry, which is the foundation for 3D reconstruction to recover 2D images to 3D. Yeah, so given this physical world, let's say this is a real capture, and we place two cameras. So one is here and another is here. So with these two cameras, we take two photos, and we want to rely on the image alone from the cameras to infer the geometry. So everything we have is about the images. So how can we do this? The underlying assumption is here for a single 3D point over here, when it is projected onto multiple image planes like here and here. So if we can track the multi-view consistency, say if we will know the point here, and if they are all correspond with this real 3D point over here. So with this information, we can recover the 3D information. So that's a basic assumption, and we will begin with the real-time 3D modeling. Yeah, so still, we will introduce some specific techniques that use to recover the 3D information. And the first is cost volume. Because we only have image observation, but we really want to recover the 3D, the depth. But the point is, we don't know anything about the environment. So that's why we have to set a set of hypotheses. Or we can think, we don't know the ground truth, but we have multiple guesses, and we predict the probability for each depth plan. Then we will get the estimation. So that's an assumption. But we can set a set of plans, and then we will build a 3D volume tensor. Let's say here we have the x dimension, we have the y dimension, and we also have the depth dimension, right? The depth dimension means we have multiple hypotheses, and we're going to regress the probability for each hypothesis. So that's an overall idea. And a multi-view geometry or cost volume trying to transform this image to this image, and using the depth hypothesis. So if we can find the consistency in pixel, then we can have the prediction. We can have the surrogate task to predict the probability of each depth plan. Yeah, so that's a basic idea. But the point is, because we are processing the 3D cost volume, there is one extra dimension, right? So there is one extra dimension for the tensor processing, then it will be very heavy for the computing system. So that's why if you are going to produce a high-resolution image, or you have you have many depth hypothesis plans, then we will got intractable computing requirement. So that's why this is my first work. We can build the city-scale high-definition map by multi-view geometry, and we design the new algorithm. We show few reconstructed blocks using the point cloud, and this is indeed why with such new algorithm design, we can allow the multi-view geometry to process the image data efficiently. Yeah, so again, the novelty or the main assumption of our work is, okay, of course we have to process all the depth range from near to far because we don't have any prior information about the environment. But we can have a balance. We can strive for a balance for building this tensor. So here, when we're trying to build the cost volume, we have the near and we have the far end. Typically, we don't know anything about the near and far. And that's why if we use just a few depth plans, depth hypotheses, then we will lose accuracy because we don't have information, but we only discretize the environment by few depth hypotheses, right? So we will lose the accuracy. But if we use so many hypotheses, then the computing requirement will be significantly high. So that's a problem, and we're going to strike a balance between these two. Yeah, so our solution is a multiple stage cost volume. And again, initially we have the five depth hypotheses. We decompose them to 2 stages. So in the first stage, we only work on 3 depth plans. And we will have a plan reduction from a single tensor, and we can build the kind of, you can think it's a coarse cost volume. So with this coarse cost volume, we roughly know where is the depth plan. And with this prior knowledge, we do a second round search. So because we already know roughly where is the depth plans, so in the second stage, we only need to build a very thin cost volume, and we search around the initial guess. And we also tap into the lower encoder feature. So that's why you can see we can increase the depth resolution. So we call this as a volume pyramid. Yeah. And here is the result. So this is a traditional multi-view MVS net, and this is ours. So we improve the formula of cost volume, and you can see we can build a higher spatial resolution depth map, and we require less compute. And this is the results. So the numbers. Oh, sorry. So we improve all metrics based on that. So we improve the depth accuracy, we reduce the GPU memory requirement, and we also improve the runtime, and which serve as a foundation for multi-view geometry in very recent periods still using this kind of design because it runs really efficient for computing systems. Yeah. So this is the demonstration of, say, we have the 3D point cloud of the environment, and we can convert them to vector map. And this is really useful for, let's say, when you use the Google Map for driving, and this kind of vector map will have you to understand the road infrastructure. Okay. Yeah, and the next part will be 3D perception and the full spectrum of the 3D perception and understanding. So let's have an overview. Given images, and the target goal is to have a semantic 3D map because that will be the useful format for robotic perception system. So start from input image. We are first doing the feature extraction and mapping. And only with the matched results, we can try to estimate the camera pose because when we do the capture, we don't have anything about it. We have to understand where we got these images. So only with this, we can estimate the camera pose, and then we will do the sparse reconstruction and do the dense reconstruction, and finally do semantic understanding. But we have introduced the work, multi-view geometry, all cost volume, but it only serves one step of the entire spectrum. So that's a problem because the 3D reconstruction is a very traditional problem and very, very difficult. So that's why people are trying to decompose it to multiple stages and solve them individually. But the point is, it's not differentiable, and we cannot scale. Let's say in current foundation model, people are trying to think, okay, can we have a differentiable large-scale model, and we just ask it to learn by data. But if it's this fashion, so the reconstruction process will be very tedious, and it requires a very long processing time. So which means it's not scalable, and it's also non-differentiable. So the next point is, can we really build a single framework, say ideally a transformer architecture, and we can input with the image data and output the semantic 3D map. So that's the overall goal of the second work. Yeah, so our work published in the last year New Waves called large spatial model. So we have this work. Say, given images, we have a transformer, we build a 3D, and we then flatten from 3D to 2D. We compare with another image, and we backpropagate the loss to update the differentiable reconstruction model. So that's the overall idea. We found it functioned very well, and ideally it should work, right? But we tried many engineering efforts to make it work well. Yeah, so let's take a little deeper look at how it works. So get image. So what we first initiate is geometry. You can think that's just like a set of point cloud. And we initiate the geometry based on pixel alone, 2 images, and we only rely on pixels. And we will have a, let's say this is a kind of point cloud. We know roughly where is the points. And next, we regress the set of 3D Gaussian, because 3D Gaussian is a detailed point cloud. And with the 3D Gaussian, we can really model the details, the detailed texture of the environment. And we regress a set of 3D Gaussians, and then we have a rasterizer, which flattens from 3D to 2D. We render, we predict the target view, and we compare with the ground truth image. And we use differentiable rendering to update the loss. So here, the only supervision from data is we have to know the relative pose about the input. So we don't need the depth annotation, and the only requirement is about the relative pose. So we call it as sparse annotation. And so this kind of sparse annotation is relatively easy to obtain by using traditional algorithms. So which means we can scale up the data curation very easily. Yeah, so in the previous slide, we introduced how we can build the 3D reconstruction differentiable to make it differentiable. But we still don't have any semantic information about the work, right? So ideally, when we have the data for robotic system, it's better, it's a semantic 3D map. So in that way, say the planning module and the control module can easily extract the useful semantic or instance information from the visual input. So our work also extends the 3D reconstruction system to semantic 3D reconstruction. So the underlying assumption is the same. for a single 3D semantic point here, when it is projected to multiple image plane, should also look consistent, right? So that's, again, the same assumption, and we're trying to track this consistency. So here, we extend with a parallel branch. So give images, we have a multimodal 2D model. Let's say it's from clip encoder. So we extract the 2D feature map. And after we extract the feature maps, we tokenize them into a set of 2D tokens. And then we fill them to the cross-model fusion. And again, we regress a set of 3D Gaussian. But here, we regress extra feature vectors, say here, F. So the feature means the underlying 2D image feature, and we learn the prediction of such semantic feature by using the rasterizer to flatten them to 2D. So now we have predicted not only RGB image, but also the feature map. And we compare with the ground truth data so that we can train the model differentially. And here, that's during the inference stage. Given image, we have a transform model. We predict the semantic 3D map. And we have the RGB images. We have the features. We have the depth. So what we can use for the features? So the user can give a test query. Say we want to find the wall, the floor, the chair. And we use the clip text encoder. We got the feature embedding. And we compute the textual visual similarity. And we decode them to semantic 3D map. Yeah, so that's a use of the semantic lifting. And it will be definitely useful for the robotic perception system. Yeah, so overall, this work collects the sparse 3D data and have a single 3D ML model. And we use neural rendering as objective function to optimize the model. So we train one model, and it can generalize to zero-shot setting. Say you collect 1,000 of scenes to train your model, and when you give a new image, the unseen image, it can adapt zero-shot. Yeah. So any questions so far? Yeah.
In the 19 case, I say you have a deep deformation, so the all input is RGB or just RGB.
So you mean?
Yeah, this case.
You mean this one, right?
19.
19.
So I say they have the deep mapping, right?
Your depth map, yes.
Yeah, deep mapping. So that is an interesting question that for the input image.
Mm-hmm.
So it is what is the format? It's RGB or RGBD?
Yeah, so like the traditional 3D Gaussian, the short answer is RGBD. And the long answer is, so like the traditional 3D Gaussian splatting, we only use 2D images, and we can also rasterize the depths, right? Because it can learn the depth field in a self-supervised way. So same principle applied to our work.
Yeah, and another question is, you say you have the, for the last page, you talk about you did semantic, right?
Yeah.
On the 2D. So for this semantics, do you use some of this information or
just a feature?
Just
Yeah, you can think, say, if we use the clip visual encoder frame by frame, there will be some inconsistency, right? Because that's from a 2D model. So, but in our work, you can indeed see the feature is really consistent. So that's why you can think of the 3D lifting from 2D to 3D, make the feature consistent in 3D. Yeah, go ahead, please.
Actually, you say that you use the cross-view constantly.
Yes.
And so, yes. So you apply this in 2D and then densify the Gaussian?
So you can see this is the same principle, like the tracking the pixels, because you can think the feature vector just a high-dimensional vector like the pixels. So in that way, we only have to render another set of prediction, like we have a high-dimensional output than pixels, and we can track the consistency on feature vector. Yeah, so that's the current work so far, and let's view some interesting demo. Yeah, so this is the real capture data. So we collect the data with Dr. Aaron Han, and we go to a lab space. We use just use iPhone. We capture about 200 images about the device, and then we run the 3D reconstruction algorithm. And after we have this 3D model, we can render the video in any new view. And this model is ideally for robotic simulation. Let's say if you want your robot that works really well in your lab space. So ideally, you want to deploy your model first in the simulator to get familiar with the environment, right? Because you really don't want to test the zero-shot generalization ability. Maybe it will fall. So that's why having this 3D model, you can put it to the robotic simulator software, and you allow your robot first to get familiar with the environment, and then you can deploy your model. Yeah, and this reconstruction was carried out by my student Zhiwen from CSE department. And so if we make a visualization about the 3D Gaussian, it's indeed just a set of 3D points, but for each 3D point, it's not a single point. It's a ellipsoid. So it's a 3D ellipsoid. You can see we use so many 3D ellipsoid to model the environment. That's the basic principle of 3D Gaussian splatting. But the point is, okay, of course we have the fancy demo. We can model the real world using a set of 3D points. The point is, it's very difficult to make the performance to be real time especially on edge devices. Let's say when you have a headset and when you have a robot system that's trying to allow it to see the real world, say from the 3D model in real time, it's very difficult. So you can see on Jetson, roughly, it can only render at 10 FPS, but the real-time performance, generally speaking, we have the criteria, let's say, it had to render more than 30 FPS or more, right? And another point is, for a single 3D environment, we require gigabyte storage for the 3D model, so which is quite non-scalable. The point is, so because we use so many 3D primitives to model the environment, which means we have a lot of 3D points. And for each 3D point, we store them explicitly, and we use a high precision floating point to store every attribute of the 3D point. So that's why it's very heavy. So let's say for each 3D point, we have to store its XYZ scale, color, rotation, and opacity. And for each 3D point, we use 32-bit storage. And can we learn from the machine learning algorithm to make the 3D model to be also efficient? So that's why in our second work, which is light Gaussian, also published in the New York last year, so we applied the pruning, distillation, and quantization technique to 3D, and we found it works quite well and make the model size smaller. Yeah. So let's get started by reviewing the traditional or the typical neural network pruning. So given a fully connected neurons, MLP, the idea is find the importance score for each connection, and we prune the connections, right? So for 3D, is it possible to measure the significance or importance of each 3D primitive, and then we prune the less important ones? So that's a high-level idea if we want to apply the pruning technique to 3D. Yeah, so here we have to quantify the importance score for each 3D primitive. And this is our formula. So let's say this is a camera, and this is the pixels, and this is the existing 3D Gaussian. So if we want to quantify the importance of this 3D Gaussian, what we can do? We consider how many rays was hit with the 3D Gaussian. And we also consider the Gaussian, its opacity. And we also consider its volume size. So consider all of the three factors together. So we call the first one as hit count, and we call the second term as Gaussian opacity, and the last is the Gaussian volume. We consider all of the three, and which formulates the significance score for this quantification. So here, that's the results. Very interesting, because 3D Gaussian is a very nice work, but the point is there exists a lot of redundancy. So you can see, so when we prune the Gaussian by almost 60%, here we prune 60% of the 3D Gaussians, and we still preserve the visual fidelity, right? So if we look at this point and this point, so they have almost the same SSM value, but at the same time, we improve the rendering speed. Say we improve the rendering speed from about 200 to about 300, so 50% faster, right? So the high level idea and takeaway of this page is 3D Gaussian is highly redundant. We can perform roughly 60% without any performance drop. Yeah. And the next part is about distillation. So distillation in traditional machine learning algorithm is about, say, how to distill a teacher large model to a student small model. But we hope they are functionally well, say in maybe the same way. So in 3D Gaussian, what we are doing is, okay, so we have a heavy 3D model. So it has a many degree about the spherical harmonics to model the appearance. And the student is a low degree spherical harmonics. We trunk the highest degree of the spherical harmonics, and we're trying to distill the information from the teacher to student. So it also works very well. And the last part is quantization. So quantization is a very popular technique in traditional machine learning. And but here for 3D model, for 3D Gaussian model, we first do a clustering, and we have the codebook, and we assign the original 3D model to each codebook. We assign such index, and we only need to store the index, so which functionally very well. And we update the codebook repeatedly. So we also weight this process by the importance score, because not every 3D point is equal, right? Because some 3D Gaussians are more important, so we have to consider them a little bit more. Yeah. So with these three techniques, you can see, okay, let me see if I can remove. Okay, great. Yeah, so let me play this video again. So you can see in the bottom, that's the original 3D Gaussian model, and in the top, that's our model. We reduce the model size by 15 times, and we almost keep the SSM value from roughly only 1% degradation. Yeah, so which means it works very well, and we have this kind of apple-to-apple comparison on this video. Yeah, and oops. Yeah, so if we look at the number, we reduce the model size here from original 3D Gaussian about 15 times, and we improve the rendering speed on the x-axis about 100%. Oh, sorry, it's 60%. Yeah, and that's a number. And the takeaway of this work is also very simple, but I think it's very useful to make your 3D model smaller. You can consider the machine learning techniques, and you can transfer them to graphics and design the same criteria to define how to improve the quality, the speed of your 3D model. Yeah, and the next part is about variant language model. I think it will be also very interesting. So variant language, as we all know, variant language model or VRM take the monocular or single image data as input, and we also give the language instruction. So we hope the language model can answer what we are asking and give the reasonable response. So that's an overview of language model. But if we want the language model to really understand the 3D problem, let's say for a robot, when we deploy the language model on the robot, it really should understand about the physical world and then make response. So traditionally, people have to rely on the depth sensor to encode every pixel to 3D point cloud to answer any 3D related questions. Or you can use traditional reconstruction algorithm, let's say 3D reconstruction or SLAM, to first build the 3D map and then feed the 3D map into the variant language model. But they are non-scalable. Let's say if you are doing the pre-training your variant language model from web scale video data, so you don't have the depth sensor, right? And if you want to have a 3D reconstruction first, then you have to wait roughly 1 hour for each data point. So that's also impractical. So is it possible to have a way, say, we can allow the language model to understand the 3D world in almost real time, just like how variant language model works with the normal image data and text data. So here, this is an example from Stanford, from Dr. Li's lab. So they designed a benchmark to test the visual spatial intelligence of the very language models. And they have a bunch of video data and have a lot of questions to test how the very language model works with such visual data alone. And here, that's a summary about this benchmark. Say we have the object count, we have the relative distance, and we have the appearance order, relative direction, route plan, and room size, roughly eight tasks. And we have our algorithm. Let's first introduce the algorithm and then introduce how we curate the data. So we have again, we have the language model. Traditionally, we have the question and the molecular video input. And we encode the molecular input, traditional algorithm, use the visual encoder, say the clip, to tokenize them into the visual tokens and fill into the language token. But here we have another spatial encoder. So we have a pre-trained spatial encoder. We extract the geometry token and the camera token. And then we do a 2D, 3D fusion together. And with such fusion, so here the token are not only understand the visual appearance, but also it understand about the spatial information from the visual input alone. So with this architecture, then we can train the model end to end. So that's why you can see few of my previous work trying to build a better spatial encoder. So because if it can work for arbitrary video data, and the performance, say the performance can be in real time, then it will be very efficient to improve the generative model for understanding the physical world. So yeah, so here that's a result on they have the actual spatial encoder with the visual feature together, visual encoder together to have the language model to understand the physical world. And we also design training data, large-scale training data, more than 100K. So we have defined these tasks together, and we train the model. And finally, this is the answer. So let's first look at the GPT and Gemini. So their performance is really well for the evaluation. So about 34 and 45. So in the bottom row, that's our results. So we have a 7B model with the training and with modifying the architecture. So you can see we got the results higher than GPT and Gemini. So this can be contributed to the data and model. And this is one benchmark from Feifei Li's group. And we also designed a benchmark to allow the very language model to understand about the temporal dynamics. And here, that's a result. So you can see still our model performs the best because I got to say data and model. Yeah. And so if we already know the bottleneck is about the data and model, and for the model, maybe we already reached the bottleneck. It's very difficult to have the new data for the model at this stage. If you are working on a very popular topic, then what we can do? So can we have a scalable data curation engine? So like the image, this is the size of existing image data. But for 3D model, we only have this, right? It's very difficult because traditionally, when people are trying to deliver a 3D data, we have the RGB camera, and we also have a depth sensor. And we also have to annotate the semantic information of the environment. And only in this way, we can produce one data point for 3D learning. So that's a point. And can we rely on the existing video? Say you have so many videos from YouTube. So can we do the annotation from the video and then provide such 3D annotation to your generative 3D model? So here is our answer. Let's go to the next part, human and environment data curation. Okay. Yeah, so because this is a paper published recently to News, and it's a data pipeline paper. The high-level motivation is very simple. We combine the modern model-based prediction. Say so many people have the foundation model. Let's say the segment anything, the Q1 from Alibaba Group, and can we directly combine it with the traditional 3D reconstruction algorithm to make the prediction to be accurate? And here is our answer. We combine a lot of multimodal foundation models with the traditional 3D algorithms, and we create the data from multiple video data sets, only video annotations. We don't have other information, and combine them together. And here, this is our data scale. So we have a very rich annotations. And we also have a very large amount of data annotations. Yeah. So with this data, we convert the raw video from YouTube, from any benchmark data, to the usable format for the, say, the generative model in the future. And this is the example. So given the raw video, we estimate the camera pose instance, and we have the 3D point cloud. Yeah, because you can indeed see this is not in 2D. Everything happens here is in 3D with the temperature changes. Yeah. And the next part is about, okay, so we already modeled the environment. So can we have more focus on human? Because the machine learning algorithm, all algorithms should improve the safety, the flexibility of human, let's say, human actions. So here we have another benchmark trying to understand how human moves in real world. And we, again, curate a lot of data from benchmark, from YouTube, and we also pay to get some data. And we have a scalable data curation pipeline. So let's directly jump to the result page. So for the human, we not only annotate the 3D model, but we also have the open vocabulary or text annotation about its behavior and its detailed description. And this is another case. So we annotate the human over here. So, so in that way, we will allow the vision language model to understand how humans act in real world better. Yeah. And the next part is about the scientific data generation and apply the foundation model, say, beyond the Earth. And let's directly jump to the details. And this is also another work from this year's NeurIPS dataset and benchmark track. So we have a data, we call it as Martian world model. So for the definition of world model, first it has to produce the physically plausible prediction in the future. And we don't have the data on Mars. So how can we first create the data? 3D reconstruction. So we have the images from the Martian-surface, and we build a 3D model, render the photorealistic video, and then in turn to improve the world model. That's a hell of an idea. So here, the Martian rover, it have a navigation camera. For each data point, it will have a stereo capture, say 2 images, left and right. So we use these 2 images to build the 3D model, and have this 3D model, we render a video. And with this video, we improve the video generation model based on the conditions. So that's an overview of this work. And let's see the real demos. So we get the data from NASA's, and we got a single image as input. And we define how the future happens. And I mean, just the camera control. And let me maybe jump to this picture. Yeah. Yeah. So first get the single image, and define how camera moves, how the agent moves, and we can simulate the future based on how camera moves. And our data create all existing, all possible data from Martian rovers. And we build a 3D model, and we render the video, and we use this video to train the world models. Yeah. Yeah, so my view is, because this physical world is in 3D, and we have the AI agent, so that's why the AI agent have to see in 3D and then make decisions with the physical world. So we have to see and then reason and make decisions, and we have also to synthesize a lot of data. Currently, we can indeed see there are many progress in the foundation model for autonomous driving, for the ChatGPT, right? But for the real world safety, let's say when you drive a Tesla, the critical case is, say, if there is some rare case happens, can your robot, can your car really understand this scenario and then make the right decisions? So that's why my research work will focus on about some critical case, some rare data generation, and then improve the policy in such rare cases. So that's why we can see an example. So we have this simulation data from Kala it's about a very typical and a very common crash, right? Traffic crash. So it's very easy to understand by human. But if we're going to prompt the most powerful foundation model from Google, the View 3, so let's see what will happen. Okay, but suddenly the vehicle just got changed, and no one knows why this happens. And if you are driving your Tesla, you definitely won't cross just like this, right? So that's why, based on the data curation and the policy training, so my future work will focus on how to have a better simulator to simulate the edge cases and how to improve the policy model on that corner case scenarios. And the next part is, so can we distill? Can I? Yeah. Can we transfer the human knowledge from the egocentric video to a robot? So we can immediately see, so capture, because currently there is one bottleneck. So how to create the useful robotic data in a scalable way. So we don't have the accurate answer. But we have so many humans. We have billions of humans, and we also have the egocentric devices. So we got this egocentric video. So how can we transfer this kind of multimodal information from human to robot? So that's also will be my research focus. Simulate the data and transfer the multimodal data to robot. Yeah. So I gotta say, I cannot make anything without the collaboration with my teams from all of these institutes. And I also want to say thanks for the attendee here to attend this meeting. Yeah, so any questions?
Yeah, thank you, Dr. Chen. Any questions? We have about 7 more minutes to the end of the seminar. Any questions?
Sorry?
So you mentioned about 3D Gaussian splatting.
3D Gaussian splatting, yes.
Yeah, like Gaussian work. That's an interesting one.
Thanks.
So I just saw that the rendering happened using the NVIDIA's A6000 GPU and frame rate like increased from
100.
2x, yeah.
Yes.
2x. So what is your perspective when we want to do that rendering on like, edge devices? Is it possible to get the real-time rendering?
Okay, so your answer is on the modern GPU, we have more than 100 FPS. And can we achieve such real-time performance on edge devices, right? Okay, so I gotta say the short answer is yes. Just based on how to reduce the model size. And say if you directly convert the 3D Gaussian to Ponca, then the rendering speed will be definitely real-time. And you can also convert the 3D Gaussian to mesh. And with the rasterization pipeline from the traditional computer graphics model techniques, so it will be also definitely in real time. But if you are using 3D Gaussian, then I gotta say maybe a little bit hard, difficult, but you can strike a balance between, say, the performance and the representation. Yeah.
Thank you.
Any question? Yeah.
So in your second talk, you mentioned like pruning the primitives can enhance the performance.
Yes. Oh, I didn't see improve the performance. I mean, just improve the rendering speed.
Okay.
Yeah.
So I was so because in the third talk is about creating the data bench to the benchmarks to training the models.
Yes.
So I was wondering if there are like relevant similar analysis that try to reduce the size of the benchmarks, which can also enhance the training process.
You mean reduce the size of benchmark, right?
Yeah, the size of.
So you just point out a very interesting and a very important direction. It's about data distillation. So how to distill the large-scale data? Of course, yeah, will be a lot of redundancy into a smaller data size. But that's beyond my scope. I just know about. Just know this area. But it's definitely a lot of researchers trying to think in this way, because let's say from Tesla you have the user data from say so many vehicles every day. So the first point is filtering, and then how to distill, how to continuously improve your existing model. So I gotta say, like this big tech company, they will definitely have some technique to distill the huge amount of data to say just compact format. Yeah, but I don't really know about the details about these techniques. Yeah.
I see. Yeah, maybe a following question is like, so in your fourth talk is you mentioned about the training for the corner cases.
Yes.
I was wondering like if you also think about how to enrich the training set for those corner cases, because those things rarely happen in the real life. So
you just point another critical area. So as we call it as corner cases or long tail cases. Okay. So the point is we are not able to collect the scalable corner cases, right? So how can we build a post-training technique that preserve the domain knowledge from the foundation model, but also adapt it to such limited corner case data? So that's from the algorithm side. So I don't have a concrete solution here. But you're going to define the matrix, what's corner case. And you also have to define the physical plausibility from the generated content. Then with the matrix, and you can have say many data, and with the data and matrix, you will measure the performance of your model. So I gotta say, because in these areas, improve the foundation model on rare cases is kind of new. So we are trying to develop the matrix first.
I see.
Yeah.
I see. Okay, thank you.
Probably one or two more questions. Any final questions?
I have a question.
Yeah, for sure.
So when you have a good generative model, usually you can convert that into a good algorithm for compressing video, right? So are people looking at next version of MPEG that may be used, that may use like a generative model and then compressing the difference between the prediction and the true?
You mean compare the difference between different generative models?
So generally a running theme in information theory is that when you try to compress anything like an image or any source,
video, yes,
you want to try to predict the source and compress only the difference between the prediction and the true value, because the entropy of that is a lot smaller.
I see, yeah.
And the real problem in not being able to do better is that your prediction is usually not that good.
Yes.
If you use simple models.
Yes.
But it looks like you guys have like really nice generative models for video.
Thanks. But first of all, this video is kind of rendered from the simulator, so it's not predicted.
But if you go to the Martian-surface thing, for example, right?
Yeah.
That's actual, like you train from a whole bunch of images, but you can render something in 3D.
True.
So imagine I have to send a picture from Mars back to Earth.
I see.
That communication link cannot support a lot of bandwidth.
True.
You want to really compress as much as you can, right?
Yes. I gotta say, for the static content, there will be definitely some patterns that we can explore to reduce the bandwidth requirement. But for the dynamic actors, let's say, of course, for Martian, there are almost no dynamic things. But on Earth, so if they have some dynamic actors, I think that will be more important, and it's kind of difficult to compress the data about the dynamics.
But on the whole,
the whole,
you can get a lot of compression.
For sure.
Right?
And we are also considering another point. Say you have so many generative content, say from Dr. Reddy, right? But how can we trace the source